Okay, let's do another example. Let's consider like a ceiling fan. So we got the hub right here, and then connected to the hub are going to be four identical fan blades. So let's say that each fan blade is a length of 66 centimeters and is a width of 15 centimeters. And let's say that each fan blade is a distance of 10 centimeters from the axis of rotation. Okay, and so as this thing is spinning, we're going to assume it's spinning at a constant speed of 20 revolutions per minute. Okay, so if you do the math, that comes out to be 2.09 radians per second. Okay, now, if we were to turn it off, it's going to be decelerating. So if we turn off the motor, then the angular acceleration is going to be minus 0.05. No, sorry. It's going to be minus 0.0912 radian per second squared. Okay. So the question is, okay, you also need to know one more thing. The mass of each fan blade is going to be equal to 650 grams. So what I want to know is how much power does the motor have to exert in order to keep it going at constant speed. Okay. So how much power does the motor have to exert to keep it rotating at constant speed? Okay. And so you think about this, and you think about it, and say, well, how do we answer that? Well, we know if you're going at constant linear speed, it's going to be force times velocity, right? So this is angular, so that means it's going to be torque times omega. Okay, remember I said that all these angular variables work the same way. So all we have to do is now find torque, because we know what the omega is. That is going to be 2.09 radians per second. So we just need to find torque. Okay, now how do we find torque? Well, torque we know is I alpha. So if it's slowing down due to air resistance, then that means that if we can find I and the alpha, I gave the alpha, that would be slowing down if you turn off the motor. So the motor has to keep it going, it has to be overcoming this torque right here. Okay, and so that's the torque. So all we got to do is figure out what is the I. Okay, so to find the I, let's look at one fan blade here, and the blade is a width of 15 centimeters. It is 66 centimeters long, and it is offset 10 centimeters, so the axis rotation is right there. So and there's four of these things. So the total I is going to be 4 times the I of each fan blade. So you look at it and say, well, the fan blade is pretty much like a rectangular thing. Well, a rectangular object rotating around its center, okay, we know that I of that is going to be 1/12 times the mass a squared plus b squared. Okay, this is not rotating around the center, it's rotating about a spot here, r, away from the center. Well, parallel axis theorem. That means this is going to be equal to I naught plus m r squared. Okay, so all we need to know is what is that r? Well, the r is going to be from the center over is 33 centimeters, and an extra 10 centimeters, so it'll be 33 centimeters plus 10 centimeters, so that's 43 centimeters. Okay, so that means that I is going to be 4 times 1/12 m a squared plus b squared plus m r squared. Okay. Well, we can actually factor a couple things out of here. So this is going to be 4 times m times a squared plus b squared over 12 plus r squared. So I is 4 times, I said 650 grams, so it's 0.65 kilograms, times 15 centimeters, 0.15 meters squared, 66 centimeters, so 0.66 meters squared. Those divided by 12 plus 43 centimeters, so 0.3 meters squared. Okay, and so I comes out to be equal to 0.580 kilogram meter squared. So now we know that the torque equals I alpha, so the torque is going to be equal to 0.580 kilogram meter squared times the minus 0.0912 radian per second squared. So the torque comes out to be equal to 0.0528 Newton meter. So that means the motor has to have a torque of opposite that 0.0528 Newton meter in order to compensate for the air resistance. So the power is going to be the torque of the motor times the omega. So the power would be 0.0528 Newton meter times 2.09 radians per second. And so the power of the motor to keep the ceiling fan going is 0.11 watts. Okay. So that's one reason things like fans are very, very energy efficient in terms of cooling it.